All right, remember I told you that the order of a reaction in K can only be determined how? Experimentally. Look, here's some experiments. No, we're not watching like a video. Here we go. Here's the reactants. We're mixing A and B, and some products are being formed. Do we care about the nature of the products? No, because they really don't fit in the rate law. Our job is to determine the rate law. Okay? The rate law. What is the general form of that rate law? Write it down to break down.
The initial rate or the...
Yep, we're doing the initial rate. We always do the initial rate. This is what I got. The rate is equal to a constant times the concentration of A raised to some power times the concentration of B raised to some power. Got it? And so this is what the experimenter did. The first time he ran this experiment, he took 0.1 molar A, 0.1 molar B, mixed them together, and saw that the rate was 2 times 10 to the negative 3 molarity times seconds to the negative 1. Molarity per second. Got it? That's how fast it was going. Then this experimenter said, I'm going to double the value of A, double the concentration of A. I'm a really good scientist. I'm going to keep B the same so I can see how A affects rate. Well, when you doubled A, what happened to the rate? It doubled. So what's the order of A? 1. Then the experiment said, now I need to find the order of B. And to do that, I better keep A constant. So he did. It was 0.2 here, 0.2 there. But he changed the value of B. She changed the value of B. Doubled B, and what happened to the rate when B was doubled? It was quadrupled. So what's the order of B? 2. The overall order for this reaction is 3. Okay, that was easy to do by inspection. I'm going to show you a way to do this when things are really stressful, ugly, and you really want to poke your eye right on out. Would that be okay?
Well, not the eye.
No.
Well, not the eye thing. That's why you always wear protective goggles.
Yeah,
We do in
Even
chemistry.
to the AP test.
Yeah, that'd probably be good.
Now she doesn't have to.
Okay, are you ready? So, what I'm going to do is compare mathematically what we just did out loud. So in order to determine A, what I'm going to do is find 2 trials where A changes and B doesn't, and fill in numbers in the rate law and solve for M. So I'm going to take trial 2 over trial 1. And I'm going to put 2 on top because it has bigger numbers and I want this to come out to be a whole number. If you did trial 1 over trial 2, you'd come out with the decimal take the inverse of that and you get the same answer. Got it? Okay. I wish I was way over here. So the rate for trial 2 is 4 times 10 to the negative 3rd. Literally just filling in the blanks here. K is, I don't know. The concentration of A in trial 2 is 2 molar raised to some value. The concentration of B in trial 2 is 0.1 molar raised to some order that I haven't determined yet. I'm going to divide that by the numbers for trial 1. Trial 1 has a rate of 2 times 10 to the negative third. I still don't know what K is. I have a tickle in my throat. Okay, I saw the kid drinking the water. It was amazing.
Try to tell you.
Mm.
Did you hear you got $10,000?
Mhm.
Keith, who was the gallon?
No, do not.
That would be.
Boy, that would hurt. Okay. All right. So I know that these two are exactly the same, so that equals 1. It drops out of the equation. Ditto here. Simplifying some terms, 4 times 10 to the negative third divided by 2 times 10 to the negative third equals 2. 2 is equal to 0.2 divided by 0.1 is 2 raised to some value. So, this is what we have here. 2 raised to what power equals 2? 1. M equals 1. M equals 1. So, the order for A is 1. Now, if you get into a situation, do you know how to solve for M? M, the log of 2, and that would belong to this one right here, over the log of 2, that would be this one right here, would get you to the same answer. Bless you. Okay, now, I did that. Let's try trial. Let's see, now I have to pick 2 trials where
3 and 2.
3 and 2, where B changes but A doesn't.
It said log 3.
And a 3 on top.
Okay. So where
2.
3 and 2? Okay. So trial 3 over trial 2. So the rate for 3, 16 times 10 to the negative third is equal to K. Now we know that the order for this is 1 times 0.2. In trial 2, the rate is 4. And B this time, or A this time is still 0.2. And B is 0.1. So this time the K again drops out, but so does the value for A. So 16 times 10 to the negative third divided by 4 times 10 to the negative third is equal to 4. A 0.2 divided by 0.1 is still 2. So 2 raised to what power equals 4?
2.
N equals 2. So our rate law is specifically rate is equal to K times A to the first, B to the second. Overall, it is 3. Okay, let's try one that is slightly more amusing. Here it is.
And for 4 equals 2, you just put 2 to the 2 squared equals 2
Yes.
to the n, and 2 equals n.
Mhm. Okay. So here we go. We have the following data. 2NO plus O2 yields 2NO2. The general form of the rate law would be rate is equal to K times NO raised to some power times O2 raised to some power. Our job is to figure out first what these are and then to go solve for K. So,
Why do they use K as a constant if K is potassium?
it's a small K. Let's see, I want to start with NO. Which trials would get me where I want to go? I heard 1 and 2. So in NO, 2 doubles and O2 stays the same. So that would be valid. That would be a valid trial. 2 over 1. Now I'm just going to put these numbers into the rate law. For trial 2, the rate law is 0.0164 is equal to K times the value of NO, 0.06 raised to some value, times O2, and O2 is 0.020 raised to some power, divided by the values in trial 1. The rate for trial 1 is 0.0041, it is equal to K. The A value here is 0.03 raised to some power, and O2 has remained the same. This is canceling, and when I make this all said and done, 4 is equal to 2 raised to some power.
Where do you get the 2 from?
A 0.06 divided by 0.03.
Okay.
M is equal to the log of 4 over the log of 2, and that is equal to 2. So we know the order for NO is 2. Okay. Is it always going to be 2 and 1 for the first one, and then 3 and 2 for the second one? No, it's not even that one here. So this one we're going to, for O2, we're going to say trial 3 and trial 1. Okay, and I chose those because this time O2 varies, but NO stays the same. So the rate for 3 is 0.0082 is equal to K, and then 3 has 0.030 to the second power times, let's see what we have here is 0.040. And for the first one, to the nth power. Okay, so this is canceling and this is canceling. 0.0082 divided by 0.0041 is
2.
excuse me. 2 is equal to 0.4 divided by 0.2 is raised to the nth power, n is equal to 1. So our rate law, oh dear, I'm out of scratch paper. So our rate law is equal to K, NO to the second power, O2 to the first power. Everybody agree with me so far?
Mm-hmm.
All right, now they ask you to calculate the rate constant. You can do that now that you know what the rate law is, because you can use experimental data and just solve for K. Doesn't matter which experiment you use, as long as you go across to solve it. I'm going to choose trial 1. The rate for trial 1 is 0.0041. K is what we're trying to determine. The concentration for NO in trial 1 is 0.30 raised to the second power, 0.03 squared, and O2 is 0.02. So K is equal to 0.0041 over the quantity of 0.03 squared times 0.02. That it's a big number. What does that mean?
It happens really quickly.
It happens quickly, yes. Okay. The value I have for this number is 228, 227.77. All right, I'm using my significant figures here. There are 3 sig figs in, oh wait, no they're not. There are 2 sig figs, so I guess 228 is close enough. All right, now the big important part here is what is the unit for K?
Into negative.
Wait.
Negative 2 times second negative 1.
Okay, and that is exactly right, because the overall order of this reaction is 3. And to find our unit, it's 1 minus 3, so that would be m to the negative second. Find the units of time in the rate, times seconds to the negative 1. Good? Okay, ladies and gentlemen, do not cry.
When you're doing that,
Hang on for 1 second, okay? Please do not cry when you do this one. There's nothing different about it except we added one more reactant.
Okay.
You still have to isolate this one, see how changing its concentration affects the rate. To do that, I'm thinking I'm using trial 2 versus trial 1. These stay the same. Then I move on to the bromine, and I need it to change while the others remain the same. Look, 3 and 2. And then for the H+, I need it to change, but nothing else to change. Which trials would that be?
4 and 1.
4 and 1. Alrighty. Why don't you solve that for me?
Nice.
Hang on for 1 second, just let me turn this
So
on.
the rate constant is 3 different